Now, just a quick blurb at the end. You can ignore this stuff over here. This is actually differential equation. That's calculus-based physics. So you ignore the stuff on the right-hand side of the board. But we know the x squared graph looks like this. If we take this part of the graph for x equal 0, x greater than or equal to 0, and I could actually write down the yellow is so we call this g of x, we call this f of x. So I'm going to do the yellow function. F of x equals x squared with the restriction that x is greater than or equal to 0. Now, if that's my function, well, I can make a table for that function. Very easy to do. We did that with the cubing function last time, so you know how this works out. If I do that with the cubing function, I get a graph that looks very much like this one, except it extends into the negative numbers because the cubing function, well, because of the way the cubing function deals with its negative numbers. This one makes the square of any negative number positive. So we have to restrict the domain here for reasons I'll talk about when we talk about this. We reverse the coordinate, we reverse the columns of our f of x table, and what do we get? We get a table for the inverse function. Okay, so if we reverse the x and y here, we get this, and that's not very hard to understand. We understood it when we did it with the x cubed. The only difference for the x squared is, though, we can't use this part of x squared, because if we reverse the coordinates here, we would get a graph down here, and then our graph wouldn't be a function that failed the vertical line test. There'd be two values of the function for any value of x. Well, we can't have that. That's not a function. So if this is going to be a function, we have to choose either this part of it or this part of it, and this is the part we choose to choose. Okay, so this is the inverse of the function f of x equals x squared with the restriction that x is greater than or equal to 0. That is, this is the square root of x function. And of course, we don't even have to really write this down. We know that that can only be defined if x is greater than or equal to 0. And what is that function? Well, just as we saw, or at least I asserted it, that the inverse of the x cubed function is the cube root of x function. Well, the inverse of the squaring function is the square root of x function. So that's how a square root function comes about in terms of graphs and inverse functions. Then we can say that, as we saw before, f of g of x equals g of f of x, which is equal to x. I don't have the absolute value sign here because f of g of x doesn't make any sense if x is negative, because g of x doesn't have a value if x is negative. So x is automatically got to be greater than or equal to 0 if this is going to make any sense. So these two are equal, and they're equal to x as long as x is greater than or equal to 0. So the condition of an inverse function to say f and g are inverse functions is to say that f of g of x equals g of f of x, which equals x. On the common domain. Now there's actually more I should say there, but I don't want to confuse the issue with this. So just take this as saying you got to be careful about the domain. Got to be careful x is in the domain, and that g of x is in the domain of f of x, and that f of x is in the domain of g of x. Okay, more about that in class. We're just doing the support stuff here. This is the main idea. So and the other examples are f of x equals x cubed, g of x equals cube root of x. We constructed that again the other day. And we can say that these are inverses. And there are many, many others. That's just another example.